Going to the frequency synthesizer, which is a most fascinating area. My student is already put his finger up that you have only 1 hour. So I do not know how can I give this within 1 hour, but let me give you the fundamentals. I am just giving from the out of concepts that suppose you have this kind of a 1 channel and 1 channel. This is the channel 1, this is the channel 2. So, Rayleigh criteria, all these things. So, you need how to separate these 2 channels. That means this is not a good separation plan, but if you have this one and this one, so you can say it is moderately done. But if you like this and this, then you will have much better channel separations. Okay. Now think of it, I am designing say 2.4 to 2.48 gigahertz. This is the roughly 80 megahertz channel bandwidth delta F, and I have to cater to say 80 channels. So what will happen? So I will have only 1 megahertz spacing in between the 2 adjacent channel maximum, that is 1 megahertz, because you have 80 channels to be converted to be accommodated in 80 megahertz. Yes or no? Now think of it, you need a frequency tolerance. So you should require, when the requirement of spacing is 1 megahertz, then what should be your tolerance limit? Obviously in the kilohertz. Yes or no? So you need to resolve these 2 signals in the kilohertz range when the spacing is 1 megahertz. But look at the signal. The signal will be like that. I am only single side, so it is single. It will be like that. In that signal, you will have what? It is superposed with some sort of phase noise. So this phase noise will actually add with that signal, and that might go into this kind of a situations where the signals of the 2 adjacent channel, I would say the superposed signals with the noise is actually blurred your resolution. Yes or no? So you understand that I need a kilohertz level of resolution in a gigahertz channel when my channel is crowded with say 80 such channels. That means my channel spacing is restricted to 1 megahertz. Then I need that kind of a resolution. So now think of a situation that what will be your noise characteristics. This signal, so again I do it, suppose this is your signal, then if my noise characteristics is dropping in this fashion, then I am done. That means it is not, it is dropping. So that is my carrier frequency 2.4 gigahertz, and that is my offset. So within the say 100 megahertz, within 1 megahertz, 100 kilohertz offset, if my 1 by f noise or the phase noise is dropped, then I will be happy. Within this channel spacing, that is 1 megahertz, okay, if my noise drops, okay, to say 10% of the max value, then I can have a better confidence in my channel resolutions. Yes or no? Clear? So you understand the challenge of a frequency synthesizer design, that I have to accommodate large number of channels, okay, with a stringent frequency resolution or frequency separation technique, and which is always being challenged by what? Phase noise. So phase noise is added with your signal, and that will give you some kind of a blurring of the channels. So separations getting problem. So you understand this, right? So let me go with this keyword to design a frequency synthesizer. Second one, So if it is 2.4, let me go to this 2.4. So I am going to not simple things, going to say Zigbee. Are you familiar with the Zigbee? The Zigbee is a for instrumentation or for sensor wireless node. Then you are getting say 16 channels. Same 2.4 to 2.48 gigahertz, 2.4 to 2.48 gigahertz, but the number of channels is 16. So what will be the channel spacing? Essentially that will be 5 megahertz. So your spacing would be 5 megahertz. So if the lowest frequency is 2.4 gigahertz, then the next one will be what? 2.405. The third one will be 2.410 and so on. So 5 megahertz spacing is there, and the channels 2.4 to 2.48 gigahertz with 5 megahertz spacing. There are 16 channels. One channel will transmit say your the intensity of the light, another channel may be the frequency of the vibration, another channel may be the temperature and so on. So you are having 16 channels. Normally for measurement of environment measurements you need 4-5 channels, that is good. So 6 channels for biomedical applications is good enough for that, but 16 channels are there in a Zigbee protocol. So you understand that how to now, this is 2.4, right, and another one is say 2.405. So that is my FC. So how to extract the signal from the carrier at 2.4? That I have to introduce an LO close to 2.4, yes or no? Then the difference of that will give me the IF band, yes? If you want to make this extract the signal from this channel, what you have to do? You have to give a local oscillator frequency of close to 2.405, yes or no? Then accordingly you are got a 16 channel which is 2.48 gigahertz. So you have to give a local oscillator frequency of 2.48 gigahertz, yes or no? So you need to generate the local oscillator frequency the same 5 megahertz spacing, 2.4 to 2.48 gigahertz. Who will do that? I told you to design a VCO. That VCO can develop this 2.4 with a tuning range of this fine tuning and etc. and so on. But that frequency should be stable. There must be some sort of a lock-in or the stable frequency characteristics. So you need some kind of a phase lock loop or frequency phase frequency loop lock loop kind of a structure, PFD or PLL kind of a structure, where both the frequency and the phase should be synchronized. Now why you require both the frequency and the phase should be synchronized? Now how would you do that? That your frequency of your oscillator or the frequency synthesizer is matched at that moment with the carrier signals. You have to do something. So only thing, you have a reference clock which will come from your crystals. The crystal is not oscillating at 2.4 gigahertz. Crystal is operating say at 5 megahertz. So what we will do that? The output frequency, you will have a divider to divide that to the reference frequency and then compare with whether the reference frequency is matching with your carrier frequency, divided carrier frequency. Now if they are matched in the frequency, you say that is locked. My answer is incomplete here. Observation is incomplete. Other thing is the phase. Suppose there is a horse race going on. So one of the rider is started a little delayed, but they are having the same speed. What will happen? The two horses, horse 1 and horse 2, their rider would have a constant gap. So your phi becomes constant, and differentiation of the phi is the frequency, d phi dt is the frequency. So here that delta f might be 0, mind it, delta f might be 0, that is the frequency difference might be 0, but delta phi is non-zero. That is, they have started initially, there is a phase delay. Now, when it is locked, both things should be 0. That means delta f and delta phi should be 0 simultaneously. That is called phase frequency locked. Clear? So, that is the essence of designing any kind of a frequency synthesizer. So, who will give me that reference? I have to always check the reference is coming from a very stable oscillator called the crystal oscillators. Okay? Clear? Now, all I mentioned is the building blocks of the frequency synthesizers, that you have the PFD, that is the phase frequency detector. Then if there is a phase difference between the two signals, what will happen? You have to measure the phase difference by some way. Suppose this is the signal. I am drawing the signal in that way. Suppose this is the signal. And another signal is little leading, like that. So, what is happening? This is delayed by an amount this. So, that is this is the same frequency, both are at same frequency 2.4, this is also 2.4, but this is delayed by a phase delta phi. Clear? This is 0, this is pi, this is 2 pi. So, delta phi is the difference. So, now this delta phi has to be made 0 for a phase lock-in condition. Then look at here, you have done exclusive OR gate, yes or no? That is when 1 0 is 1, 0 1 is 1, but 1 1 0 is 0. So, this one you will get a pulse, and this one you will also get a pulse. That is, in one cycle you will get 2 pulses. So, you can say that your pulse width of this gets modulated with the duration of the phase difference, yes or no? If the phase difference is more, then you have larger delta f, that will introduce more pulse width. Now, this is the PFD output. So, I will say that sometime it is not required an exclusive OR gate, AND gate will be used, because for a complete cycle I need only one cycle, one pulse, not 2 pulses. So, I am just giving as an example, you can use an exclusive OR gate, have 2 pulses, but you understand what is pulse width modulation proportional to the change in the phase. Now, that pulse, now if you trigger a current source, you have a current source, you trigger that with that pulse. That means the current pulse will, now current source will be on for that delta phi time, corresponding time. What will happen? This current will flow and essentially it will charge one capacitor. So, my capacitor will be charged by a constant current source for a duration which is proportional to the difference in phase, yes or no? So, the voltage that will come up from this will come as a charge pump output, that is called the charge pump, okay? That is actually charging the capacitor. Now, this capacitor voltage, it is called the control voltage of your VCO. So, you understand the VCO. So, you understand that VCO you will now will be controlled by this voltage. So, when VCO voltage is finite, then what will happen? Accordingly, your frequency will change, the varactor variation will be there, the frequency will be changed. Again, that frequency will be divided and compared to my reference frequency crystals. And then what will happen? They will try to reduce that one. So, at some time you will find the delta phi becomes 0 and the charge pump voltage becomes 0. So, control voltage is now 0 and it will give a oscillation at the free running frequency of the oscillators, yes or no. So, that is called the lock-in conditions. Very simple bare-eyed view of a phase frequency or the PLL or a frequency synthesizer architectures. Now coming into that, I want to have the frequency hopping from 2.4 to 2.405, 2.405 to 2.41, 2.401 like that. So I need a 5 megahertz spacing. How do you do that? You should need one divider. So suppose it is reference frequency is 5 megahertz, clear? If it is 5 megahertz and your free running frequency is 2.4 gigahertz, clear? Then if your frequency divider is say 480, calculate 480 into 5, how much it's coming? 2.4. So this 2.4 is being if it is, you just quickly calculate, this is 480 and it is 2.4. So 2.4 divided by 480, how much it's coming? 5 megahertz. So 5 megahertz is coming from the divider output and then compared at the PFD. So that is the 2.4. Then what will happen? I want to make it to the next one. So I will increase my counter from 480 to 481 and like that. So you will divide it the same frequency, suppose this is 2.401. So divided by the next n plus 1 and then again it will be 5 megahertz because 5 megahertz spacing in f reference into n plus 1 will be your running frequency, that is the VCO frequency. So in that way you can actually changing the divider number from n, n plus 1, n plus 2 and so on, like n plus 16, you will have 16 channels which will come over, but they will all be translated into 5 megahertz in the loop to the PFD and compared with your reference clock which is coming as 5 megahertz. Clear? So the frequency that is coming from the VCO is getting divided by a programmable divider. So essentially the function of the divider is to make the division such a way always the reference frequency is equal to the reference frequency, so that comparison can be done. So that is the essential things of that. So this is the transfer function of this model. So if you have this theta out, theta in, then you know that the charge pump will have this transfer function, KVCO acting as an integrator, so KVCO by S, then divider is a number, so 1 by n, and the filter, the KCP, that is your after the charge pump, the current is actually charging the loop filter, the capacitors which will be normally second or third order loop filters, that will have a transfer function. So finally this is the transfer function of the frequency synthesizers. So once you get that one, then you understand that you have this input signal. Now what I say that if there are two signals, F reference which is at say 5 megahertz, okay, and this is my input signal, that is the VCO output divided by n, this is the signal, and if there is a phase difference between them, then it will turn us as the I up. If there is leading, that gives you I up, or it is down, it is giving the I down. So that will actually essentially charge my capacitors, and that is the charging profile of the capacitance which is fed from the filter to the VCO to control the frequency of that. Now look at here, how do you make your PFD? The phase frequency detector, that means you should always control the phase of that comparable with the reference one. So this is your reference frequency, and that is the coming divided, there is a FVCO divided by frequency synthesizer coming to 2D flip flop, okay. And then if there is a phase difference of that, then 1 0 it will give you the, if it is up signal is 1, then the down signal is 0 and so on. So accordingly the duration of the current will charge up your capacitor, so the output of the filter will give a ramp. So, what is the total phase can offer is pi 0 to 2 pi. So, if there is a difference is 2 pi, then accordingly the voltage I s integration of dt 0 to t, that will be the total charge to the capacitor. So, it will ramp up to this. This is for I up and this is for I down. So, in this case you will have those control voltage which is fed to the VCO. So, you are finding it out, this is the V in and the VCO, and this is the up and the down current, and finally when they are locked, then we will find this is going to be almost 0. But there is a big thing, that there is a dead zone. When the two phases are exactly matches, then the charge pump becoming little bit of confused in what state it will go. Then actually you introduce some kind of a delay in the system, in this system, so that the dead zone can be avoided and the system becomes stable. Otherwise, when both the phases become locked, then ICP, the control voltage or the charge pump voltage will become where voltage it will take. There will be uncertainty in the systems. So, you introduce some kind of a delay, and that will a small at the cost of small phase, because you need 0 to 2 pi. But you introduce some kind of a delta phi phase offset, I would say that, where actually you know that it is locked conditions, but you give a delay to avoid this dead zone problem. This is a very classical problem of this, where the charge pump will be at haywire, where voltage, because almost 0 voltage, 0 phase difference means they should have no voltage, but at that case there will be uncertainty in the controlling of this VCO. So, you need some sort of a, and this is how this structure works. How it is done? Suppose the up signal is on, okay? I say it is a constant current source. So, this up path is on, so this current mirror is feeding that current, VDD is find the path, and the current is now going to the filter, yes or no. So, this is the up, and the up switch duration is depending upon the phase difference, and this is when the down pulse, that is when phase is lagging, then the down is on, that means this transistor 1. So, your filter is discharged through this path to the ground. So, you will find both the up down pulses coming out of the charge pump, and its duration of charging and discharging depends on the phase difference, by which the input reference frequency, input RF frequency is lagged or lead with respect to the reference frequency. So, that is the typical charge pump, and then you have this kind of a third order passive loop pass filter, that is called the loop filter, which is used for your filter design. And look at the transfer function of this, then you introduce some poles in it, so that the stability is satisfied. It might cost the bandwidth of your loop bandwidth is sacrificed because of the introduction of the pole, but that will improve the stability of the cell. So, you can make second order filters, but it is always desirable to go for a third order filter introducing another extra pole, that will give you the stability of your things. But I caution you, when you make some sort of simulations, then second order and its corresponding transfer functions derivation will be much easier, but this is not a realistic design. Actually, you can prove your design by considering a first order, second order filter, because 1 by s from your KVCO give you another order, but introduce another order in the loop filters, that is a more realistic case of this. So, this is the way how you should go into the design of this. And then another thing, next block is the divider. In the divider block, you know that in the divider block you can actually think of a series of divider cell, okay, and combinations of divide by 2 or divide by 3 will introduce that divider 480 or 481 and so on. So, that will I will come in my later half of the talk, how to design this divider and then introduce this frequency which is comparable to the reference one. So, I would say this is the 2 by 3 2 by 3, it is 2 or 3, 2/3 divider cell. So look at here, if there are 8 cells, then what will be the maximum divisions? Is 2 to the power 8 like that, to half, then 1/4, then this way you can divide. If there are 3 cells, then you calculate it will be much more than 4000 something. So you have a combination of divide by 2 and divide by 3 in that divider block, so that you can actually attain this 488. That is the way how the divider, I will go to that, just you wait for some time. And this is the some sort of initial results. I would say that 2.4 to 2.48 gigahertz, and that introduces some kind of a division ratio of 480 to 495 to cater to the need of 2.4 to 2.48 for Ghibli applications with 16 channels with spacing of 5 megahertz, and which consumes 9 milliwatt of power, the total consumption of the frequency synthesizer. And this is the first snapshot of the chip, and you will find this is the typical spectrum of this, and then we make the controllable watt count to the divider, and see this is the divider ratio. So if we find out the reference frequency of that and so on. So this is with the, it is the background of this frequency synthesizer design, and then I will go in details to the development of frequency synthesizer by phase, combating our initial problem of phase noise.